Stand on the coast of the ancient Roman world, and you're looking at structures that have endured salt water, storms, and time itself for nearly 2 millennia. Then look at a modern structure, perfectly engineered, code-compliant, failing within a human lifetime. That contrast should bother you, should force a question most people avoid. If we are more advanced than any civilization before us, why do so many of our buildings age like disposable products? This isn't nostalgia. It's a pattern. Across history, people built under pressure, extreme cold, relentless heat, earthquakes, scarcity. And they solved those problems with methods that were simple, local, and brutally effective. Then, in the modern era, many of those methods didn't just fade away. They were dismissed, regulated out, or replaced by systems that prioritize speed and uniformity over endurance. What's unsettling is that modern research is now circling back, quietly confirming that many of those primitive techniques were grounded in real physics. Thermal stability, moisture control, structural flexibility, applied with precision, not guesswork. This isn't a story about old versus new. It's about durable versus disposable. And once you see the difference, you start to recognize how much practical survival knowledge has been buried under the idea of progress. Let's start with one of the most misunderstood housing strategies ever used. In parts of Eastern Europe during the Little Ice Age, winters were not inconvenient, they were lethal. Families didn't have the luxury of wasting heat. Every mistake cost fuel, time, or lives. So instead of building upward and exposing themselves to wind, they built downward. By digging roughly 5 feet into the ground, they reached a zone where temperatures remained relatively stable year-round. This wasn't luck. It's a known geothermal principle. Below the frost line, the Earth buffers temperature swings. In extreme cold, that stability becomes survival. Archaeological reconstructions have shown that even when outside temperatures dropped drastically, these semi-subterranean homes maintained livable interior conditions without continuous heating. That's not insulation in the modern sense, it's strategic placement. What mattered wasn't just digging a hole. Builders understood soil stability, drainage, and slope angles to prevent collapse. They avoided water tables and positioned entrances to reduce exposure. Every decision reflected an understanding of how heat moves and how wind steals it. Modern housing often fights the environment with energy. These homes avoided the fight altogether by stepping outside the worst conditions. For decades, the white fragments inside Roman concrete were treated as flaws. Poor mixing. Inconsistent technique. That assumption fell apart once researchers examined what those fragments actually do. Roman builders used quicklime in a way that created reactive pockets inside the concrete. When cracks formed, and they always do, water entering the fracture triggered a chemical reaction. The material effectively healed itself by filling the crack with newly formed minerals. Modern concrete doesn't behave that way. It prioritizes predictability and speed, but once it cracks, the process accelerates toward failure. Water reaches internal reinforcements, corrosion begins, and the structure weakens over time. The Roman approach accepted that damage was inevitable. Instead of trying to eliminate it, they built in a response mechanism. It's a fundamentally different philosophy, designing for recovery, not just resistance. It's the difference between something that survives stress and something that quietly deteriorates under it. When industrial materials became widespread, one property dominated thinking: strength, harder, stronger, more resistant. Those qualities define progress. Then those materials were applied to older buildings, and the results were destructive. Traditional masonry relied on lime mortar, a material intentionally weaker than the surrounding bricks. It absorbed stress, allowed movement, and, most importantly, let moisture pass through and evaporate. Walls could breathe, preventing water from becoming trapped. Modern cement changed that. It sealed joints, trapping moisture inside the wall. When temperatures dropped, that trapped water froze, expanded, and forced the brick faces to fracture. The damage wasn't immediate. It built slowly, invisibly, until the wall began to fail from within. The earlier approach accepted that materials should not all be equally strong. Some elements were designed to fail first, protecting the rest of the structure. That principle, controlled failure, is still one of the most important ideas in engineering. In earthquake-prone regions, the instinct to build rigid, immovable structures works against survival. When the ground moves, rigidity becomes a liability. Traditional East Asian architecture approached the problem differently. Wooden frameworks were assembled using interlocking joints that allowed controlled movement. Instead of snapping under stress, the structure shifted, absorbed energy, and redistributed forces. Some buildings were not even rigidly anchored to the ground. They rested in a way that allowed subtle motion, reducing the stress transferred into the structure itself. This principle, allowing controlled movement, is now central to modern seismic design. But it was practiced centuries ago using wood, geometry, and an understanding of how energy travels through a structure. The lesson is direct. Resisting force is not always the best strategy. Sometimes survival depends on how well you can move with it. Long before electricity, people in extremely hot regions faced the same problem modern cities struggle with: how to remain cool without turning the environment into a heat trap. The solution was architectural, not mechanical. Wind-catching towers directed airflow into buildings, using pressure differences to move air naturally, when combined with underground water channels. The system cooled incoming air through evaporation before distributing it throughout the structure. This wasn't a passive feature. It was a functional system built into the design of the home. Modern cooling often relies on sealed environments and continuous energy input. These older systems worked by enhancing natural processes already present: air movement, temperature, gradients, and evaporation. The difference lies in whether a building works with its environment or isolates itself from it. In medieval construction, some builders developed walls consisting of two separate layers with a gap in between. That gap, often filled with air, acted as insulation. Air is a poor conductor of heat. By interrupting the path through which heat travels, these walls reduce temperature transfer significantly. The concept is now standard in high-performance construction under different names: thermal breaks, cavity walls, but the underlying idea hasn't changed. The insight was simple. Not every improvement comes from adding material. Sometimes it comes from strategically removing it. Walls made from compacted earth or clay mixtures behave differently from thin, modern materials. They absorb heat during the day and release it slowly at night, smoothing temperature swings. This property, thermal mass, creates stable interior conditions without constant energy input. These materials also regulate humidity, absorbing excess moisture and releasing it when the air dries. That balance contributes to both comfort and structural longevity. The reason such methods were sidelined had less to do with performance and more to do with standardization. Earth varies from place to place, making it harder to regulate in an industrial system built on uniformity. But variability doesn't mean inefficiency. In many cases, it means adaptability. In traditional longhouses, smoke from indoor fires passed through the roof structure before escaping. Over time, it coated the materials with compounds that resisted pests, slowed decay, and improved water resistance. The system wasn't designed solely for preservation. It was a side effect of heating. But it demonstrates a broader principle. Outputs from one process can strengthen another. Modern design tends to separate systems, heating, ventilation, preservation, into isolated functions. Earlier approaches often combined them out of necessity, creating overlapping benefits. That mindset, looking for multiple uses from a single process, is still relevant wherever efficiency matters. Water is one of the most persistent threats to any structure. It erodes, seeps, freezes, and expands. Ignoring it leads to failure. Historical builders rarely ignored it. They studied how water moved across land and shaped their foundations accordingly. Gravel layers, drainage channels, and sloped terrain directed water away before it could accumulate. Rather than relying on systems to remove water after it appeared, they prevented it from becoming a problem in the first place. This approach requires observation and planning, but it reduces long-term risks significantly. It's a reminder that prevention often outperforms correction. Gothic builders wanted height and light without massive, heavy walls. The solution was not stronger walls, but a redistribution of forces. By transferring structural loads outward through external supports, they reduced stress on the walls themselves. This allowed for thinner walls and larger windows without compromising stability. Modern engineering confirms the effectiveness of this approach through load analysis and modeling. But the concept is straightforward. Forces need pathways. A structure that manages those pathways intelligently can achieve more with less material. The pattern across all these methods is consistent. They don't rely on excess. They rely on understanding. Heat, moisture, movement, airflow, gravity, these are constants. Ignoring them leads to failure, no matter how advanced the materials. Working with them creates resilience, even with simple tools. Modern systems often compensate for design weaknesses with energy and technology. Historical systems reduced the need for compensation by addressing the problem at its source. That doesn't mean everything old should replace everything new. It means the mindset behind those solutions still matters. So the real question isn't which technique is better. It's which principles we've overlooked. If this breakdown changed how you think about buildings, survival, or history itself, subscribe and share this with someone who takes durability seriously. There's more to uncover, and the next insight might change how you look at the structures around you every day.